All right, welcome to section 12.2 on exponential functions. Our objectives are introducing exponential functions, recognizing graphs of exponential functions, relating percent change in exponential functions, computing compound interest, modeling with exponential functions, and finally recognizing the natural exponential function. What are exponential functions? Well, a function represented by something like f of x equals c a to the x, where a is greater than 0 and a cannot be equal to 1, is an exponential function with base a and coefficient c. Otherwise stated, we assume that c is going to be greater than 0. Okay. Now, in our formula, we said a is going to be greater than 0. That's going to be called a growth function. Okay. Now, if a is between 0 and 1, though, it's going to be a decay function. So all really kind of depends here. So a is greater than 0 is kind of the key, but there's two pieces that could happen. So the first one is it's a growth factor when a is greater than 1, and it's a decay factor when a is between 0 and 1. So basically a decimal. Okay, and so here we see an exponential growth, and a is greater than 1. Here we see an exponential decay, and here a is between 0 and 1. So those are the two key differences. So we're supposed to evaluate f of x for the given value of x. So let's first state this. Well, this is greater than 1, so that's going to be a growth. And that's between 0 and 1, so that's going to be a decay. So when we see a growth, we should get a number that's going to be bigger than 10. And when we see a decay, we should see a number at less than 4. So that's going to be kind of our key thing. Now we're just plugging in 2. That's just plug and chug in your calculator. So we're going to take and plug in, well, I guess this case 3, that one 2. So we're going to take 4 to the third and then times 10. So that's going to give us 640. And as I said, we should be at a bigger number than 10 because it's a growth. Now, with this one, we should get less than, so we plug in 2. That's going to be a fourth times 4, so that's going to give us 1, and that is less than 4. Now, for each table, we're supposed to determine whether f is a linear function or an exponential function, and then find a formula for f. All right, so here at time 0, we're at 64. And then if we move up 1, what have we done? Well, it looks like we divided by 4. Then if we move up one more, we've divided by 4 again. If we move up one more, we've divided by 4 again. And I would assume number 4 would be 1/4. And so this looks like it's some kind of a decay function where 1/4 is going to be our a value. And so our c is going to be our initial factor, 64. And so if we go through here, 64 times then 1/4 to the power x, and that should be our exponential decay function for this set of data here. What about for b? Well, b, what we have is we're going at 0, it's 3. And then at 1, we've gone up by 2. 2, we've gone up 2. 3, we've gone up by 2. So it looks like this is linear function and we're going up by 2 each time. So our initial 0, 3, that's our intercept. So remember, when you're doing intercept formulas, we have the formula y equals mx plus b. So we know b is going to be 3, 3. So what we have to do is we have to figure out our slope. Well, we knew the slope is 2 because we went up by 2 each time, and because we went up over 2, or up 2 over 1, up 2 over 1, and so we just get 2x plus 3. Again, that was the 3 was our initial point at 0, 3, and we went up by 2, 2, 2 every time we went up 1, 1, 1. So that's why we have the 2 over 1. Okay, and so that would be our linear equation for this graph, or this table, I should say. All right, so let's stop there and come back for some more.